In this video, we're going to continue our discussion about two-dimensional motion, and specifically looking at projectile motion and the kinematic equations that we use to solve projectile motion problems. Let's start out by doing another example. The question says, what is the magnitude and the direction of the final velocity? The height of the cliff is 150 meters. In this problem, we can see that the object is given some initial velocity that is directed above the horizontal, and our projectile is going to go through a path something like that. What we're being asked for is to find the magnitude of the final velocity as well as the direction. Remember that we always specify the magnitude and the direction of the vector, where the direction is relative to the positive x-axis. So we're trying to find v and theta. Let's look at what information that we know so far. I'm going to place my origin at the bottom left, and that's where I always put it because that allows all my positions to be positive. So that's my origin. You'll notice therefore that the initial height would be y naught, that's 150 meters, and the initial x position, x naught, is 0 meters. Let's see what else we know. We're given 30 meters per second. What variable is that? Hopefully you yelled out v naught. That's v naught, the magnitude of the initial velocity. And 20 degrees would be theta naught, the initial angle of the velocity. Remember that when we use the kinematics equations for projectile motion, this value, v naught, never goes directly into those equations. What goes into those equations are the components of v naught. So the next thing we probably want to do is figure out what are the initial components, or the components of the initial velocity. We know that vx naught and vy naught can be found by using our basic understanding of trigonometry. In other words, vx naught is simply found by taking the magnitude v naught and multiplying by the cosine of theta naught. In the same way, vy is v naught sine theta naught. If you plug in the values, and I'll just tell you the answer here, you can check me to make sure I'm right. What I got for vx naught was 28.2 meters per second. And what I got for vy naught was 10.3 meters per second. Notice that those values make sense because theta is less than 45 degrees. We know the x component should be bigger than the y component. Okay, so we've identified everything we know at the beginning of the problem. Let's finish identifying what we know about the object the instant before it hits the ground right here. Well, we definitely know the final height is 0. Notice that we don't know how far it went in the x direction. We also don't know how much time it took to get there. We do know the final component of the velocity in the x direction because that's just vx naught. So in other words, we already know that vx is 28.2. However, we do not know vy. Remember that we never say it's 0 because we're talking about the instant the object gets to the ground, not once it hits the ground. Here's the strategy that you want to remember. Remember that the kinematics equations only deal with components. So since we're being asked for the magnitude and the direction of the final velocity, the first thing that we have to do is find the components of the final velocity. You'll notice we're halfway there. We already know vx is the same as vx naught, so 28.2, but we've got to find vy. Once we do that, then we can find v and theta. Look at the formulas for projectile motion and see if you can figure out what formula would be the best to use to find vy. Well, let me tell you what I picked. I picked that vy squared is equal to Vy naught squared minus 2Gy minus y naught. The reason that I picked that formula is that it has Vy in it, which is what I'm trying to solve for, and it also does not have t in it because I don't know the time. Now, most of the time with these kinematic equations, you can do it some different ways, but this is the most direct way to solve the problem. I'm going to go through our standard problem-solving techniques. So I'm going to cross out what's 0. And let me rewrite that now. I have Vy squared is equal to Vy naught squared. I got minus 2g times negative y naught, so I get plus 2g y naught. At this point, I can just take the square root of both sides. I get Vy is equal to the square root of Vy naught squared plus 2Gy naught. Again, we always want to solve algebraically before we plug in any numbers. Now, there's one key thing that we can't forget, and that is the plus or minus. Because in physics, we've got to pick the correct sign based on the problem. You'll notice that our object is traveling downward, so we already know conceptually that we're going to want to pick the minus solution. Let's go ahead and plug in the numbers. So we've got plus or minus, and we're now just going to plug in the values that we had from before. So we've got 10.3 squared plus 2 times 9.8 times y naught, which is 150. What we end up with for Vy is plus or minus 55.2 meters per second. And again, we now have to pick the correct answer. Since we know that the object is moving downward, we know the correct answer is Vy is negative 55.2 meters per second. So now we have the two final components. We have Vy is equal to negative 55.2, and from before we know that the final x component is 28.2 because it was equal to the initial. The last thing we have to do then is just go through the work to figure out the magnitude and direction of the final vector. So here's what we've got. We've got Vx, we've got Vy. We can see that Vy is a bigger component than Vx. So we know that when we're looking for V, we can see that theta is going to be a negative angle and it should be bigger than 45 degrees. To find the magnitude, we just use the Pythagorean theorem. Vx squared plus Vy squared under the square root. And I'll let you just check my answer to make sure that you agree. I got 62 meters per second for my final answer. So that's the magnitude. We know that the angle can be found by using the inverse tangent. So the inverse tangent of Vy over Vx. So if you calculate that, what you should get is negative 63 degrees. Remember that in physics, we usually leave that angle in the fourth quadrant as a negative angle because it's easier to visualize negative 63 than it is to visualize that big angle that you get if you add 360 to it. Let's look at the following conceptual question. Shoot two cannonballs at an angle of 45 degrees. One cannonball has twice the initial velocity of the other. That cannonball will go. So what we're trying to figure out here is how will the range of our projectile, remember the horizontal distance that a projectile goes is called the range. We're trying to figure out how will that change based on the initial velocity. So go ahead, pause the video, and come up with what you think is the right answer. Okay, if I were looking at this question for the first time, I would think that if we have twice the velocity, it would simply go twice as far. That makes sense to me. However, it's not the correct answer. It turns out that it will go four times as far. So physics is tricky. It doesn't always seem to follow the way that we might think it would. And so this is why we have to rely on using equations to help us with our understanding. In other words, what we want to prove is we want to prove the range of the projectile is directly proportional to the velocity squared, the initial velocity squared. So if we double the initial velocity, then the range is 4 times as far. Or if we triple the initial velocity, the range would be that squared, or 9 times as far. So that's what we'd like to show. So I would like to remind you of all the things that we've talked about over the last 2 videos. Earlier in the last video, I claimed that 45 degrees gives the maximum range. I also claimed that complementary angles give the same range. And remember, by complementary angles, we simply mean angles that add up to 90. So if I shoot it at 30 and 60, like in our diagram there, they would have the same range. The third thing that we just claimed is that the range is directly proportional to the initial velocity squared. So however I change the initial velocity, the range is going to change as the square of that. Well, in order to prove these 3 things, what I need to do is I need to be able to write x, the range, how far it goes in the x direction, as a function of v naught and theta naught. So we should be able to come up with an equation that proves these 3 claims that I've made. If you look at the equation we have in the x direction, we have x is equal to x naught plus vx naught t. What I want to do is I want to work on this equation to try to rewrite it, first of all, instead of just a component of the initial velocity, write it in terms of v naught and theta naught, but I also want to remove t from the equation and see if I can get x as a function of just v naught and theta naught. So how do we go about doing that? Well, let's start out with our diagram. We've got our initial projectile. We've given it an initial velocity of v naught at an angle of theta naught. And we're trying to figure out what the range depends on. So again, how far it goes in the x direction. As we've said, we know that x is equal to x naught plus vx naught t. And we'll assume we're starting at 0, so I can get rid of that. And now what I want to do is I want to put in for vx naught directly in terms of v naught and theta naught. Well, we know how to do that. That's just the component. It's just v naught cosine theta naught. So that's vx naught times t. But now I want to figure out a way to eliminate t in that equation. To do that, I'm going to use the y direction. So in the y direction, one of our equations is vy is equal to vy naught minus gt. And notice that because my object is starting at the same height as it's ending at, so y and y naught are the same, if that's true, then what's true about vy and vy naught? Do you know? Well, one is equal to the minus of the other. In other words, if the initial y component, let's say, is 10 meters per second, the final y component would be negative 10. Notice that's only true when the object starts and ends at the same height. So since that's the problem we're doing, I'm going to rewrite this, and I'm going to replace vy with negative vy naught in the equation. So I have negative vy naught is equal to Vy naught minus gt. I'm going to now swap the gt and the negative Vy naught. So I get gt is equal to 2 Vy naught. So I'm adding Vy naught to both sides and adding gt to both sides. Or t is equal to 2 Vy naught over g. The last thing that I'm going to do there is I'm going to put in what Vy naught is in terms of V naught and sine theta. So t is equal to 2 Vy naught, or sorry, 2 V naught sine theta naught. And I'm dividing that by g. I'm going to now take that and put it back in here, because remember, we're trying to get x as just a function of V naught and theta naught. Well, if we do that, we get x is equal to V naught cosine theta naught times 2 V naught sine theta naught over g. Or x is equal to 2 V naught squared cosine theta naught times sine theta naught. Now, I don't expect you to remember trig identities off the top of your head, but I'm going to just point out to you that whenever you see combinations of sines and cosines, remember there's almost always a way to write that in a different way. The identity that we need here is that sine 2 theta naught is equal to 2 cosine theta naught sine theta naught. So that's just one of those trig identities that you learned about when you took trig. Remember, we call those the double angle formulas. There were also the half angle formulas. So just know they exist, but you certainly don't have to know them off the top of your head. Notice that that allows me to now rewrite my final answer as x is equal to V naught squared sine 2 theta naught divided by g. So what have we learned from this? Well, first of all, notice that we've definitely proved one of the things we were trying to prove. You can see that x is directly proportional to V naught squared. Again, the importance of that is if you shoot a projectile, let's say 4 times as fast, well, that means it's going to go 16 times as far. So the range is directly proportional to the square of the initial velocity. Let's look at what else we've learned. I want to just remind you that if I'm plotting sine theta versus theta, we know what that looks like. Our sine function looks like this, where this would be 360 degrees, this would be 180 degrees. But what's here in the formula is not sine theta, it's sine 2 theta. So what does sine of 2 theta look like? Well, remember, and I'll put knots here just to make sure we're being consistent. Remember that you probably at some point in pre-calculus learned all about what happens when you put factors in different places. But here you can just kind of figure it out. If I put in an angle of 45 degrees, I'm taking the sine of 90 degrees. Well, we know the sine of 90 degrees is 1. So what this does is it ends up compressing the graph. In other words, this is now 45 degrees, and this is 180, or sorry, this is 90. So now the whole period of the graph is only 180 degrees instead of 360 degrees. So notice that one of the things we want to show is that theta naught equals 45 gives the maximum range. And we've now successfully done that because we can see that sine 2 theta naught is a maximum at 45 degrees. The other thing we wanted to show was the idea that complementary angles give the same range. And you'll notice that we've done that as well, because notice that if I look at, let's say 10 degrees and 80 degrees or 30 degrees and 60 degrees, etc., if I'm the same amount on either side of 45 degrees, I can see the value of sine 2 theta naught is the same. And therefore, I get the same range for complementary angles. Let's look at the following conceptual question. A monkey sees that the game warden is about to shoot him with a tranquilizer dart. To avoid being shot, he lets go of the tree at the same instant the game warden fires. Does the monkey get hit? Assume that the dart is fired with a great enough velocity that it at least gets to the tree and that the barrel of the dart gun is aimed at the initial position of the monkey. So in other words, we know that it's not as if the dart is just going to come down and hit the ground before it ever gets to where the monkey is. It will definitely at least get as far as the tree. Why don't you go ahead and pause the video and think about it, and then select your answer. Okay, well this one is kind of an interesting one because it turns out that the monkey always gets hit. And we don't have to know anything about the velocity of the dart, again, as long as it gets to the tree. We don't have to know how far away the tree is. We don't have to know the height of the tree. So again, maybe a little bit counterintuitive. And what we want to do is use our equations for projectile motion, our kinematics equations, to see if we can prove the fact that the monkey always gets hit. Here's the setup for the problem. Again, we're shooting with an initial velocity v naught at an angle theta naught, so we're aimed right at the monkey. You'll notice that there is a relationship between theta naught, the height of the monkey, and the distance d that the tree is away. In other words, tan theta naught is h over d, or h is equal to d tan theta naught. And as we'll see as we go through the problem, that's going to be important. It's an important reason why the monkey always gets hit. Here's our strategy for working out this problem. Really what we need to do is simply figure out how long does it take the dart to cover this horizontal distance d. So how much time does it take the dart to get to the tree? Once we know that time, we can calculate what the height is of the dart at that time, calculate what the height of the monkey is at that time, and if those heights are the same, then we know the monkey always gets hit. So let's figure out how much time it takes for the dart to get to the tree. So time for dart to get to tree. In order to do that, we're going to look at the x position for the dart as a function of time. So we know x is equal to x naught plus vx naught t. Well, what we want to know is what time, or how much time it takes for the dart to travel a distance d. So our final position is d. Notice our initial position for the dart is 0, because we'll put our origin here. And then we just get x naught t. I'm going to write this as v naught cosine theta naught, as we've done many times, times t. So t is equal to d over v naught cosine theta naught. That's the amount of time it takes for the dart to get to the tree. And now all we need to do is figure out how high is the monkey at that time and how high is the dart at that time. The equation that we're going to want to use to do that is y is equal to y naught plus vy naught t minus 1/2 gt squared. So that in general is our kinematic equation for the height of an object in projectile motion. We're going to apply that two different ways. First, let's do it for the monkey. So the height of the monkey is a function of time. Notice the monkey starts out at an initial height equal to h. Now the monkey just lets go of the tree when t is equal to 0. So the monkey's initial velocity is 0. Therefore that middle term goes away, and we just get h minus 1/2 gt squared. So that's the height of the monkey at any time t. What we want to know, though, is what's the height of the monkey at this time. So let's plug that in. And I'm also going to plug in the fact that we know h is d tan theta naught. So we have d tan theta naught minus 1/2 g times d over v naught cosine theta naught squared. So that's the height of the monkey at the time that the dart reaches the tree. So that's monkey. Let's figure out what the height of the dart is at that same time. So again, just using this equation, but now writing it out for the dart. Well, the initial height of the dart is 0. It starts down here at the origin. But the initial velocity of the dart in the y direction, vy naught, would just be v naught sine theta naught, the y component of the velocity, times the time. Remember, that's d over v naught cosine theta naught. And then we have minus 1/2 g times t, d over v naught cosine theta naught squared. Let's simplify that middle term, or that first term, I should say. Notice v naught and v naught cancel out, and I get sine over cosine, which we know is tangent. Therefore, that first term becomes d tan theta naught. The second term is still 1/2 parentheses d over v naught cosine theta naught squared. So what do you notice about ym and yd? They are identical. So once we work this out, we see that no matter what the values are that we plug in, as long as our initial conditions are met, the monkey and the dart are always at the same height when the dart gets there, and therefore the monkey always gets hit. Here's one last problem in this video. What I'd like you to do is pause the video here and see if you can figure it out on your own. I've given you all the equations. Let me just draw out the problem for you. It says a soccer ball is kicked at an angle of 27 degrees with a velocity of 15 meters per second. It lands on a hill 2 meters higher than its initial height. So let's just draw the picture. So our soccer ball starts down here on the ground. It's kicked with an initial velocity of v naught at an initial angle theta naught. And it lands on a hill. So its final position is higher than its initial position. What I'd like you to do is go through and see if you can solve this completely on your own. This is very similar to the kinds of problems you should be able to do on the exam. After you've tried it on your own, go ahead and restart the video and see how you did. Okay, so let's go ahead and work out the problem. The first thing that hopefully you did was you drew a diagram, because that's required to draw a diagram and to identify everything you know and you don't know. So here's my diagram. I've got v naught and theta naught. Our object is going to go up, which is a soccer ball in this case, and it's going to land here. And we're asked 3 different things. We're asked for how much time the soccer ball is in the air. We're asked for the horizontal distance it travels. And we're also asked for the magnitude and the direction of the final velocity. Okay, so I'm putting my origin here. Therefore, x naught is 0. Y naught is also 0. Notice that I don't know how far it goes in the x direction. That's one of the things I'm trying to find. So I'll circle that because I know I want to find that. The final height in the y direction, I know. It lands on our hill that's 2 meters high. Notice I don't know how much time it takes to get there. That's another thing I'm trying to find. I know the initial velocity, v naught, is 15 meters per second. And I also know that theta naught is 27 degrees. Therefore, I can calculate the components of the initial velocity. Remember, you always are working with the components in those kinematics equations. So v naught cosine theta naught and v naught sine theta naught. I'll just tell you what I got when I calculated those. I got 13.4 meters per second and 6.81 meters per second. Okay, what else do we know or need to know? Well, we know that the final component of the velocity is always equal to the initial component. So notice we already know that. It's 13.4 meters per second. We don't know Vy. Again, it's not zero. We don't know what it is. And ultimately, we're trying to find the magnitude and the direction of the final velocity. So that's what we're looking for, x, t, v, and theta. Now there are a couple different ways you can go about doing this problem. I'm going to solve it in the order that it was asked. So the first thing we were asked for was how much time the soccer ball is in the air. The only way to do that directly is by using y is equal to y naught plus vy naught t minus 1/2 gt squared. Notice that since we do have a vy naught, we're going to end up having to use the quadratic equation. In other words, y naught is 0, but both the t and the t squared term are not 0. Therefore, at this point, I can just plug in the values and use the quadratic equation. Y is 2.00. Vy naught is 6.81 times t. And then minus 1/2 times 9.8. I'll just do the math. That's 4.9 t squared. I'm going to now bring everything over to the left-hand side. So 4.9 t squared minus 6.81 t plus 2 is equal to 0. At this point then, you need to plug into the quadratic formula. Make sure that you do that. I do want to see the quadratic formula written out and the numbers plugged in. So in other words, t is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. And you want to then show the numbers plugged in. I'll let you guys do that on your own. I will tell you that I got 2 times 0.421 and 0.968. So here's the question. Which of those is the time you want? It turns out it's that one. It's the second time. Notice that we can't easily just get rid of one of these times because they're both positive. Why is it the longer time? Here you have to think about the problem. Notice that this soccer ball is at a height of 2 meters twice. It first gets to a height of 2 meters right there. Then it goes up higher and then comes down and hits our hill. So this first time is the time to get right there, but that's not what we're looking for. We want the time to get all the way to the hill. And that's why we have to pick the second time. Once we have the time, then we can answer the second part of the question, which was how far does the soccer ball go in the x direction? Just by using our one equation that we have. So x naught is 0, x is equal to 13.4 times that time we just figured out. And we get 13 meters. So that's the answer to part B. Part C, we're supposed to find the magnitude and the direction of the final velocity. Again, we already know Vx is 13.4 meters per second because it's simply equal to the initial. To find the y component, we just want to use Vy is equal to Vy naught minus gt. And that's all solved for what we need. We just have to plug in the values. And I'm just going to tell you what I got when I did that. You can check it on your own. I got Vy is equal to negative 2.68 meters per second. And then finally, we need to find the magnitude and the direction by using the Pythagorean theorem and the inverse tangent. And again, I'm just going to give you the final answer. Just make sure that you check it on your own and that you get the same values. For the final magnitude, I got 13.7 meters per second. Remember, the magnitude of a vector is always positive. For the angle, I got negative 11.3 degrees. Again, fourth quadrant, we leave it as the negative angle. And I can see that that makes sense, that the soccer ball was going in a direction that looks something like that when it hit the hill.